Danny Elegante from A+ College Ready, here to work the Unit 8 practice problems with you. Let's go ahead and jump in with number 1. This is a classic question where they're giving you two Ka values, Ka being 10 to the negative 6th for Ka1 and 10 to the negative 11th for Ka2. So which one is going to be the ion in the lowest concentration? The ion in the lowest concentration will not be this one, because that ion has a larger Ka than this Ka down here. Therefore, that makes this ion right down there the ion in the lowest concentration. So we can immediately get rid of choice A, we can immediately get rid of choice B, and we're left between C and D. The chance of this ion happening from the two equations, starting out with H2CO3 and getting all the way down here to CO3 2-, is a function of multiplying the two Kas together. So the Ka1 times Ka2, that'd be a total of 10 to the negative 17th, and the chances of that happening are pretty dang small. For question number 2, same data set, same Ka values, but a different type of question. So which one is a Bronsted-Lowry conjugate acid-base pair? This is the acid, and the thing it becomes is the conjugate base. Unfortunately, that is not one of the choices down there. This is an acid, and that is its conjugate base, and it turns out that, boom, D is the right answer, and so that is my conjugate acid-base pair. For choice B, you'll notice the reason that's not a conjugate acid-base pair is conjugate acid-base pairs occur on the reactants product side, not both on the reactant side. Choice C is not correct because this thing and this thing are both acids. We have an acid on the left giving up an H, and then the thing on the right, the H3O hydronium ion, is also an acid. So that would not be the answer either. Moving on to statement number 3. This is where your kids writing net ionic equations all semester long is going to pay off. For the HNO2, HNO2 is a weak acid. It is not one of the strong acids. Therefore, we would keep it together in the net ionic. Meanwhile, the sodium hydroxide is a strong base. Since it is a strong base, we would actually take it apart. On the right-hand side, it's going to form sodium nitrite, NaNO2, and water. The water stays together. The sodium nitrite would pull apart because it's an aqueous salt, which tells us that the sodium is left over as a spectator, and that's how we come to this final answer down here. The acid left together, the hydroxide pulled apart, forming water, and also forming that nitrite ion. Choice D is wrong because the sodium hydroxide is stuck together. Choice B is wrong because it separates the hydrogen and nitrite ion. You don't do that for a weak acid. And choice A is wrong because, again, you don't separate the HNO2, and choice A would be the net ionic for a strong acid, strong base titration. In order to understand this, you have to write the Ka expression. You can see the Ka expression here. And then if you were to plug this into an ice table, you would find that the Ka value, 9 times 10 to the negative 6th, is equal to x squared over 1, the initial concentration of the solution. When you find x by taking the square root of both sides, you find that x is 3 times 10 to the negative 3rd. X is also equal to the hydronium ion concentration or hydrogen ion concentration. So basically, this is the part that dissociated divided by the total concentration before it ever dissociated, and you get 3 divided by 1. The math is simple. To break it down simply for your students, make sure to show them that scientific notation numbers turn into regular numbers, and when you take a number and turn it into a percent, you move it 2 places to the right, giving us the answer of C. This is similar to the question about conjugate acid-base pairs. Hydrazine is a base, So that means on the opposite side of the equation, on the product side, it's going to have absorbed an H. Therefore, N2H4 has to turn into N2H5. Both of those choices are reasonable. However, when you gain a hydrogen ion, you take on a plus charge, meaning that D has to be the answer. This is purely a solution stoichiometry problem. The moles of LiOH is going to be equal to the volume, which is 0.0500 liters, times the molarity, which is 0.10. The moles of the HI are going to be found the same way. So the moles of LiOH is 0.005, the moles of HI is 0.03. Obviously, we have a whole lot more acid than we do base. Once you combine, that means there's going to be no base left over, and there's going to be a lot of acid left over. If there's acid left over, the pH has to be less than 7. The only one that has a pH less than 7 would be choice A, and the pH would have to be closest to 2. Now they could actually do the math here, but just know that it's enough to say there's acid left over, so the pH has to be less than 7. Number 7 is an excellent example of how does temperature affect pH. As the temperature increases and more heat is added to the system, then more ions will be formed, since breaking apart water is an endothermic process. Since more ions will be formed, that means pH will decrease. If you're creating more hydrogen ions, then the pH should go down, just like you were adding an acid. Since the pH will decrease, we can get rid of the two answers with red X's, and then the student just has to decide, is ionization an endothermic or exothermic process? It's an endothermic process, so that makes choice D the correct answer. This is a strong acid problem, and in a strong acid like HBr, all of the acid is going to ionize, so there's no need for an ice table, there's no need for any kind of Ka or anything like that. To find the hydronium ion concentration, we would go 10 to the negative pH value, or 10 to the negative 1. That comes out to be 0.1 molar. You only want to make 1/10 of a liter of that. So 0.1 molar times 1/10 of a liter is only equal to 0.01 moles. And since you know the molar mass is 80.91, we need to figure out what 0.01 times 80.91 is. And that just means we move the decimal place 2 places to the left, giving us a final answer of D. Number 9 is testing the student to see if they've ever actually done a titration or not. This is not about what is the right answer. This is more about what ain't the right answer. If you rinse a burette with water, that just means anything you add to it will only be diluted, and that's not what we want. If you add the indicator to the burette, that's not really helping matters, because you know we always add indicator to the thing being titrated in the beaker or Erlenmeyer flask. If you add acid to the burette, then when you add in the base, some of it will already be neutralized before you even start the titration. Number 10 is all about, do students understand the value of a Kb and what a base does? If methylamine has a Kb value, then that means that it is a base. So if you add a base to water, the pH should be greater than 7. That means we can automatically get rid of that answer. And then we just have to look and say, what other ones can we get rid of? Methylamine is not a strong base because the Kb value is fairly low. Choice B is wrong because bases do not increase the hydrogen ion concentration. So again, another example of finding the answers that are not right. Help your students understand how to find the wrong ones, and oftentimes they will find the right ones. Number 11 is not multiple choice. It is just simply a short answer problem, so we can work it out. The H iso represents the isopropylamine after it has accepted a hydrogen, and the iso on the bottom just represents the original concentration of the isopropylamine. Once you have the Kb expression, you could build yourself a rice table, but as you gain experience in doing these, you ought to be able to skip the rice table step and just understand that the Kb expression can be written thusly. Because 0.6 minus x is pretty much the same thing as 0.6, we can rewrite it by neglecting the x to be x squared over 0.6. When you solve for x, you get 0.0168. And remember that that is also the hydroxide ion concentration. So if you take the negative log of both sides, you find out that the pOH of this would be 1.77, giving us a pH of 12.23, because after all, pH plus pOH always adds up to 14. This question asks the student to think about the effects of a salt on pH. For many students, this is a very foreign concept. The student notes are pretty straightforward. Take the K and drop an OH. That's a strong base. Since it came from a strong base, that means it has no effect. Take the NO3, drop an H in front of it. HNO3 is a strong acid. That means the NO3, the conjugate base of it, is pretty much worthless. Since they're both worthless ions, the pH would be equal to 7. This question asks the students to really do two things. First of all, understand which ion is present in the greatest concentration for a weak acid, and then also to try and figure out what the pH would be given that Ka value. So if Ka is 1 times 10 to the negative fifth, that is a weak acid. So which species is going to be at the highest concentration? This species will be at the highest concentration. Because the Ka value is so low, very little of that molecule will actually turn into ions. That means we can get rid of this answer, and then the student just has to worry about finding the pH value. If they built themselves a rice table, and if they plugged in all the numbers, they would find that x squared is equal to the Ka value times 0.66. If they were to solve for x, x would be 3 times 10 to the negative third. And this is where their understanding of the nature of logs and how logs work. If the exponent is negative third, then that means the pH is going to be 2.5 and not 1.5. This question asks your students to understand and analyze a very standard acid-base titration curve. In this case, this is a weak acid titration curve because the pH starts relatively high. And if you teach your kids well, they will be able to recognize that the equivalence point is here at 25 milliliters, which means the half equivalence point is going to be somewhere in here at 12.5 milliliters. And what is the pH at that half equivalence point? That's where pH is equal to pKa. So if the pH is somewhere between 4 and 6, then the pKa must also be somewhere between 4 and 6. In number 15, notice this is the exact same graph as in number 14. Better to give your kids these problems all at the same time so they can analyze all the data of the same graph. You may even want to give them just the graph and get them to label the equivalence point, the half equivalence point. Is it strong acid or weak acid? And then give them these questions to practice. We already determined that the equivalence point is here at 25 milliliters. The students can actually do MAVA equals MBVB, but it isn't really necessary because you're using half the amount of base as of the acid. Since you're using half the amount of base as the acid, that means the base has to be twice as strong. So since the base was 0.1 molar lithium hydroxide, that means the acid had to be 0.05 molar. This question has a lot of reading. Help your students understand where the question actually lies. You don't know the conclusion that the student reached, but which logic statement agrees with the pH of the solution? If the pH was 7, the acid wouldn't be a weak acid. It wouldn't be an acid at all. If the pH was 1, the acid would be a very, very strong acid. In fact, if you took the negative log of 0.01 molar, you would get a pH of 2. Therefore, a pH of 1 can't even be the answer. pH of 3, the acid is a polyprotic acid. Polyprotic just means it has more than one H to give away. It says nothing about whether that acid is strong or weak. The correct answer here is D, because If you were to take the negative log of 0.01, you'd get a pH of 2. This is actually a question taken from the 2008 exam and slightly modified. If the pH was 12, that's a pretty strong base. But if you diluted it by a factor of 10, going from 100 milliliters of base to a total volume of 1,000 milliliters means you diluted it by a factor of 10, what will happen to the concentration of OH ions? The OH gets diluted by a factor of 10, which means it becomes less basic, which means it will drop from 12 to 11. So choice B can't possibly be the answer. Choice C is out because if there were more OH ions formed, the pH would actually increase. Choice A is out because if water molecules formed additional hydrogen ions because you added more water, it would also produce hydroxide ions that would counteract that effect. The pH drops from 12 to 11 because of the dilution. Number 18 is another good example of why students need to be able to analyze and think about titration curves. Give them the graph first, make them say whether a weak base, a strong base, a weak acid, or a strong acid is being titrated. Make them tell you what points S and R are. R is going to be the equivalence point, but the question asks about point Q. You're starting out with a strong base. That's why the pH is 13. You're adding acid to it over time. So why would the pH flatline? A lot of students are going to want to say C because they know a buffer causes the pH to remain constant. However, this is not a buffer. A buffer would be made of an acid, a weak acid and its conjugate, or a weak base and its conjugate, and this is not the case. Q flatlines because at this point you've added so much acid that adding a little bit more is not going to cause a big change in overall hydrogen ion concentration. In this graph, the question asks specifically about point B. What is true at point B? Well, we know that this is a weak acid, strong base titration because here's the telltale swoop, and we're also starting at a relatively high pH. At point B, that would be the half equivalence point, and at the half equivalence point, we know that that is a buffer where the moles of acid remaining are equal to the amount of conjugate base, making B our answer. Choice C is altogether wrong because we're not asking about the pKa. Get your students to watch out for tricks like that. Make sure the wording matches what they know. This question asks students to think about a titration curve. Again, if they learn what titration curves are and where the endpoint, where the equivalence point is, then they realize as you come up to the equivalence point and the endpoint, the graph goes vertical. So that adding just a tiny little bit of base is enough to cause a rather large change in pH, making A the answer. B is wrong because a buffer would not be present at the endpoint. We wouldn't have a weak acid and its conjugate or a weak base and its conjugate. At the endpoint of the titration, we're left with only one of the species. One more reason why you should be teaching your kids to analyze titration curves. They're going to want to key in on this point right here because they're used to seeing that pH is equal to pKa at the half equivalence point. But remember, we try to teach them that at the equivalence point here, the pH is going to be somewhere around 9. You want to pick an indicator with the pKa approximately equivalent to the pH at the equivalence point. This answer right here is wrong, methyl red, because I'm trying to trick the students. The students go, oh, 4.95 has to be the answer because they haven't read the question. The pH at the equivalence point is 9, therefore you would want to pick an indicator with a pKa close to the pH at the equivalence point. The point of maximum buffering capacity is where you have a large amount of the acid and a large amount of its conjugate base. That would be at the half equivalence point. At the half equivalence point, it's half acid, half conjugate base. That is always going to be the point of maximum buffering capacity. One thing to notice about these buffer questions is they're not complex mathematically. It's more asking the student to think about what's true in terms of the Henderson-Hasselbalch and what they know about titration curves. The amount of base, ammonia, is equal to the amount of ammonium, the conjugate acid. Therefore, at that point, the POH, because we're talking about the base, is going to be equal to the PKB. We are at that half equivalence point. Imagine a titration curve starting off with a weak base. Where you reach the half equivalence point, it's half base, half conjugate acid. That's exactly where we are here. The POH would be equal to the PKB. That means the POH is 4.75, which means that the pH is going to be 14 minus 4.75, and the answer ends up being 9.25. Notice that there is a major distractor in the question of 4.75, trying to catch the students off guard. They report the PKB as being 4.75, and the students have to think of how PKB relates to POH. Notice this is the same set of conditions as in number 23. We've got a buffered solution where the amount of NH3 is equal to the amount of NH4. When acid is added, what will happen? Well, some of the NH3 will absorb the hydrogen ion and turn into NH4. So at that point, the NH4 is going to be in a greater concentration, and the NH3 is going to be less concentrated. In that case, the amount of NH4 is going to be greater than the amount of NH3. It may help to teach your students this question in light of a titration curve. The blue mark on the graph represents the half equivalence point, which is where we start out at. The moles of NH3 are equal to NH4. If we add some acid added is actually the x-axis, which means we're going to move farther to the right. At this point, point A on the graph, that was all NH3. At the equivalence point, point B, that's going to be where all the NH3 has been turned into NH4. So if you're adding acid from the half equivalence point, you're going to move slightly more towards B, meaning you'll have less NH3 and more NH4. Same data set as before, same question stem as before, except now it wants to know what is the net ionic reaction that will happen. The H plus will combine with the NH3, giving you NH4. C is not right because the strong acid would have been pulled apart. D is not right because it's just ridiculous. And A is not right because the A plus doesn't mix with the NH4. The A plus mixes with the NH3. 26, again, is more of a short answer question. So they should write an equation. They should build a rice table. They should write out the Ka expression. When they substitute from the rice table into the Ka expression, they will get x squared over 1 minus x. We neglect the x to avoid having to use the quadratic, leaving us with x squared over 1. X would be 0.105. Take the negative log of the x value, which is our hydrogen ion concentration, and the pH will be approximately 0.98. This question would also be a really good example of when you can neglect the x and when you can't neglect the x. Technically, because the concentration is 1 molar and the Ka is kind of big, 1 times 10 to the negative 2, technically you shouldn't be able to neglect the x. Of course, on the AP exam, you'll always be able to neglect the x. This would be a good time for your students to use the quadratic, find an answer for the pH there, and compare it to the pH they get when they neglect the x. For instance, if you were to plug this into the quadratic without neglecting the x, you would get that x is equal to 0.0995. Not a huge difference, but a little bit of a difference. And the pH of that would be 1.002. Compare that to the answer that you get when you neglect the x, and you can see that the answers are very, very close. Number 27 is a question that a lot of students and teachers will get wrong. The first time I answered it in a hurry, I got the answer wrong. You'll find that the students will think that the strongest acid, the one with the lowest pH, should require the most milliliters of the base. and that helps identify where their gaps in logic are, where their misunderstanding of acids and bases are. We teach them that MAVA equals MBVB. If all 4 acids are 0.1 molar and they all are 10 milliliters, that means they all have the same number of moles. To reach the equivalence point is where we add the same number of moles of base as there are of acid. Since the moles of base are the same and it's all the same strength of base, all the acids will require the same amount of base. Question 28, same data set. The strong acid is the one that totally ionizes. In other words, for a strong acid, the hydrogen ion concentration or the acid concentration is going to be 10 to the negative pH value. And 10 to the negative 1.0 power is equal to 0.1 molar. So only acid B matches up like that. The other ones have to be weak. The only way to produce a buffer is to titrate a weak acid with the strong base NaOH. Titrating a strong acid with the NaOH will not give you a buffer. It'll give you conjugates that are absolutely worthless. Therefore, number 29 is basically the exact opposite of number 28. Acids A and C and D are all weak acids. Acid B is the only strong acid. Therefore, acid B is the only one that will not give you a buffer of some kind. And finally, this is a good pictographic representation of acid and base. They can tell that the NH4 plus is the acid and the NH3 is the base. All they have to look at is the relative concentration of the NH3 molecules and the NH4 molecules. There are 7 NH4 molecules while there are only 5 NH3 molecules. This goes back to a previous question asking about the buffering of NH3 and NH4. If the pKb of NH3 is 4.75, then at the half equivalence point, the POH is going to be equal to the pKb, which is 4.75. If the POH is equal to 4.75, then the pH has to be equal to 9.25. That would be at the half equivalence point, where the amount of NH3 and the amount of NH4 are the same. Since the amount of NH4 is greater, that means we've moved to the right of our titration curve. Again, if you look at this problem as looking at a titration curve, this midpoint here is the half equivalence point, the point at which the amount of NH3 is equal to the amount of NH4. If you move to the right at all, then the amount of NH3 goes down and the amount of NH4 goes up. And that's what this picture shows, the amount of NH4 being greater than the amount of NH3. There are 7 NH4 molecules and only 5 NH3 molecules. Since we have moved over to the right, now imagine being here at the purple line. The purple line shows us that the pH should go down, so the pH should be less than 9.25, and that is the answer.